right. Thank you guys for all coming today. We're gonna go forward with what we've been doing in chapter 4. So the plan today is to actually finish chapter 4, which is dealing with different aspects of molecular structure and bonding, and then you'll have a homework assignment on that that's due Sunday. So this should take us through all of it today. The exam is just about wrapping up. There's just a couple more time slots still going on now or later this evening. So I'll have some information next week about how we did in the first exam. If any of you want to talk to me individually about your exam results, please let me know and we can set something up. All right, and as is tradition, we're going to do our 1 hour per day guaranteed work habit Wednesday, talk about some things related to study habits and things in this course. So what I want to talk about today, and this is so we've talked a lot about the value of doing multiple homework attempts, ideally doing all 4 homework attempts every week as a way of practicing the material and helping you reinforce your learning. What I was also curious about was, when are you guys doing the homework assignments? I had a suspicion of when most of the homework attempts were being done, but I wanted to confirm this and put some numbers next to it. So I did figure out in Blackboard how to actually go through and track when all the homework attempts are being done. And what I found was perhaps not too surprising. So in this last homework assignment that was due on Sunday, the previous Sunday, chapter 3 homework, there were 19 total attempts, so that's a little bit less than 3 per student. So again, we want to get that number up a little bit higher if possible, but not too bad at this point in the semester. But what I noticed is that out of these about 1,500 attempts, almost 1,000 of them were done on the very last day when the assignment was due. So basically about 65% of the homework attempts were done on the very last day. Even more revealing was that almost 50%, about 44.5%, were done after 6 p.m. on the last day. So basically within the last 6 hours before the deadline at the very last minute. Now I'm not naive. I know this is how students work, and I certainly followed this pattern a lot when I was a student as well. But I think there are some advantages of doing the homework attempts earlier and spreading them out throughout the week. So I want to remind you of some of the value of doing that. So one is that if you do some early homework attempts throughout the week, you can come in either to office hours or to tutoring and get some help on the more difficult questions. And then for the later attempts, you'll hopefully be able to do better because you've addressed some of your questions, and you'll be able to test yourself on whether you've actually learned those topics or not. If you wait till the very end, you don't really have the advantage of doing that because you basically just have to do all the attempts right in a row. The other problem with doing all the attempts right in the row is there is the possibility of burnout. So if you're trying to cram in 4 homework attempts at the very last minute and just do them one after another, that's a lot of problems all at once. And you're not going to, most likely, you're not going to have the same level of focus and concentration at the end of that as you do at the beginning. So if you do one homework attempt at a time, you're going to spend more mental energy on each one, learn more from each one, and they'll be, I think, more valuable in that respect. And I also think, in general, in this course, and the whole point of this 1 hour per day guarantees that I've been sort of going through the whole semester is that in this course, a little bit of effort every day is better than a feast or famine mentality. So if you're trying to retain information for the whole semester, remember that this class builds on itself. We have a cumulative final exam. Most of you are going to take Chem 2 and Organic, where a lot of these same topics are going to come up again. If you want to retain the information that you learn in here, it's much better to space it out and learn it gradually as opposed to spending a few hours cramming in a bunch of stuff all at once and then forgetting about it until the next Sunday when the next assignment is due. So I want to continually emphasize the importance of doing a little bit of work every day, and as part of that, I think it would be helpful for a lot of you to spread out your homework attempts a little bit more, not wait till Sunday to do all of them, and hopefully we can see some improvement there, and that might hopefully also lead to improvements in your learning and retention. All right, so that's what I want to talk about today. So just some food for thought to think about and hopefully help plan your weekly study a little better. It's important to still do the homework attempts. I'm glad to see that we're doing them, but I think our timing could certainly be a little bit better. So what we're going to close with in chapter 4 today is the last of our bonding theory. So we spent a lot of time last time, most of the last lecture, talking about valence bond theory, which is the idea that when atoms form covalent bonds, you would have atomic orbitals or hybrid orbitals on one atom overlapping with atomic orbitals or hybrid orbitals on another atom and forming bonds. And that works pretty well, and it correlates very nicely with the molecular structure aspects that we learned at the beginning of this chapter. But the question is, so why do we need another bonding theory? Well, the reality is that valence bond theory does not, in many cases, tell us the whole story. There's some things that are left out. And one way to reveal this is to think about a very simple molecule, O2. So if we were to draw the Lewis structure of O2 and then use valence bond theory to predict some things about it, what you would get is just a double bond, and then you would get 2 lone pairs on each oxygen. And then we will predict from valence bond theory that this double bond is 1 sigma bond and 1 pi bond, as we talked about last time. All right, so that's sort of what valence bond theory would tell us about O2. And one of the things that valence bond theory would tell us, which again, it always originates with a Lewis structure, which typically assumes pairing of all the electrons, we would assume in the structure that there are 0 unpaired electrons. That basically we have 4 electrons that are paired in the bond, and then we would have these 4 lone pair electrons that are also, again, paired up all in sp2 type orbitals, but no unpaired electrons in this structure. And one thing we haven't talked about yet, but one of the things that the number of unpaired electrons determines for you is the magnetic properties of a substance. So we didn't really discuss this yet, but basically there are 2 limiting magnetic properties. So if you have 0 unpaired electrons, the properties you would predict would be called diamagnetic. All right, so there's 2, and the other one we'll talk about is called paramagnetic here in a second. So we would predict that oxygen is diamagnetic, and what that means physically is that it's going to be weakly repelled by a magnetic field. So we would expect that oxygen is going to basically not interact very much at all with magnetic field, or if anything, be weakly repelled by it, but not have a strong interaction. And this would be the case anytime you have a substance that has 0 unpaired electrons, whether it's an element or a compound. If it's diamagnetic, 0 unpaired electrons, you would predict that in the presence of a magnetic field, not much is going to happen, or it will just be weakly repelled. Now let's go and do a virtual experiment and see what actually happens when oxygen interacts with magnetic field. So I pulled up this video, which is linked in the notes. Let's go full screen so we can see it. All right, so let's go back a little bit. I think I let the cat out of the bag a little bit, but let's see what happens when we pour. So what this guy's going to do is he's going to take liquid oxygen, which is not particularly safe to play with, but he's doing it correctly. He's going to pour it through a strong magnetic field. And what you'll see is that the oxygen sticks there between the 2 magnets. So it's suspended by the magnets, so basically it's attracted to the magnets. We would not have guessed that if it was diamagnetic. And it's going to basically stay there until the oxygen boils away. It's liquid oxygen, so it's going to become gaseous oxygen pretty quickly. So that's what he sees for oxygen, which is, again, runs counter to what we would predict from valence bond theory if it was a diamagnetic substance. Now the next one we're going to do to sort of show you the contrasting behavior is let's see what happens when we actually do use something that's diamagnetic.
I hope you'll join us again soon for another experiment.
Don't they do another experiment? Yeah, so there is another experiment. So he jumped the gun and was... All right, anyway. All right, so here's liquid nitrogen, which is diamagnetic, and what you'll see with liquid nitrogen is that it goes straight through. So liquid nitrogen, that's oxygen. It sticks to between the magnets, and then liquid nitrogen, which she's going to do here again in a second, I believe. Oh, he's doing oxygen again, sorry. But anyway, there was a brief moment there earlier. Let me rewind to it. The woman on the right, she does liquid nitrogen. So liquid oxygen sticks between the poles, liquid nitrogen goes straight through, which is what you would expect for a diamagnetic substance. So that sort of shows the contrasting behavior of these substances in a magnetic field, which is again because oxygen and nitrogen have 2 magnetic properties. But the key point here is that when you do experiments on liquid oxygen, what you find is that even though valence bond theory predicts diamagnetic behavior, it's actually paramagnetic, okay? So what we have, again, is a situation where the prediction and the experiment don't match, and that means that our model is not perfectly complete. It doesn't tell us everything we need to know. So we need a better model to describe the bonding in these molecules to be able to understand why is O2 paramagnetic, or how we actually predict that with a more refined model. So the model that allows us to do this, as we'll see, is called molecular orbital theory. Now, molecular orbital theory is based in quantum mechanics, so mathematically it's very complicated, and for anything but the simplest of molecules, it can be very complicated as well. And so essentially what we're going to do for molecular orbital theory is we're only going to focus on it for very simple diatomic molecules, so O2 being one of them, or N2, H2, things like that just have 2 atoms involved. Otherwise, it becomes excessively complicated. If you take more advanced chemistry courses, you'll start talking about molecular orbital theory for more complicated systems. But we're going to talk about some of the basic principles of molecular orbital theory, and then how to use it to make predictions about the bonding and magnetic properties in simple diatomic molecules. So the key parts of molecular orbital theory is, one is that you have mixing of atomic orbitals. Now we saw that in valence bond theory you had mixing of atomic orbitals as well to some extent, but what we were doing in valence bond theory was we would either mix the atomic orbitals on just the central atom to make hybrid orbitals, and then we would overlap those with other orbitals on the outer atoms. But basically what you still had in valence bond theory was orbitals on one atom, orbitals on another, and then some region of overlap where the where the electrons would be shared in the bond. In molecular orbital theory, what you do is you're going to take the atomic orbital wave functions from each atom, and they're going to be mathematically combined with each other. And these are going to be linear combinations, meaning they're going to be, the wave functions are going to be added and subtracted from each other. But the key point is that we're not going to form individual orbitals on each atom anymore. We're going to form delocalized molecular orbitals. So we're going to form a set of new orbitals that don't belong to one atom or another, but are delocalized over the entire molecule. So the molecular orbitals that we generate in this way, they don't belong to each atom, they belong to the whole molecule. They're delocalized over the whole molecule. And so we're going to form a new set of molecular orbitals that are going to have different energy levels, different degeneracies, and things like that we're going to go through today. Now, in terms of which atomic orbitals can mix with each other, one thing that has to be true is that the atomic orbitals that mix have to be similar in energy to each other. So only orbitals which are pretty close to each other in energy can actually mix. So you wouldn't expect a 1s orbital and a 2p orbital mixed because they're very far apart in energy and they're just too far apart to interact with each other. And as is true for all the bonding theories we've been talking about, the atomic orbitals that matter are going to be the valence orbitals. So really when we're mixing atomic orbitals to make molecular orbitals, the ones that are going to actually be consequential are going to be the valence orbitals. So the valence orbitals from one atom, the valence orbitals from the other atom, those are going to be the ones that we mix together to make these delocalized molecular orbitals. So just like before, we're going to primarily focus our attention on those valence orbitals. So when you make linear combinations of atomic orbitals, anytime you mix two atomic orbitals together and make molecular orbitals, there's going to always be two types of molecular orbitals that form. One is called a bonding orbital, and one is called an anti-bonding orbital. So when you make a bonding orbital, the wave function that you generate, the molecular orbital wave function, which we'll abbreviate as capital letter psi, is going to be an additive combination of the two atomic orbital wave functions. So atomic orbital 1 from one atom, atomic orbital 2 from the second atom that's bonded to it. Those are going to mix together in an additive combination, in-phase combination, if you're thinking about it in sort of wave terms. And so that's going to give us a bonding orbital. Now, anytime, as I said, when you mix two atomic orbitals together, you're going to get two molecular orbitals. In some sense, there's a conservation of orbitals, if you will, where anytime you take two atomic orbitals and mix them, you're going to generate two new molecular orbitals. One of those is bonding, the other one is anti-bonding, and as you might guess, the way the anti-bonding orbital looks is we abbreviate it with a little star, a little asterisk to indicate that it's anti-bonding. So we would sort of pronounce this as psi star, and I can't draw an asterisk to save my life, but I will if you give me one more try. And if it doesn't work this time, I'll just throw my pen down and leave. So this is the last try either way. You might see me throw a temper tantrum, so hang on. Crap. All right.
Class over?
No, class is not over. Nice try. See if it recovers it. That's always the question. So this, let's get rid of. Just come on back whenever you're ready. Looks like it did not recover. Again? Come on. Yes. I don't know how much of it got back, but I'll fix anything that's missing before I post it. Or maybe I won't, and then you guys will yell at me and I'll do it later. But at some point I will fix this if there's anything missing. All right, so it got mad at me for taking so long to draw an asterisk. That's probably why it crashed. Let's try that again. So we did lose some things here. Let me just rewrite this real quick. The bonding orbital is going to be the additive combination of the two atomic orbitals, as we said. And then you're always going to also have an antibonding orbital, psi star, good enough, which is going to be given as the subtractive combination. So the two atomic orbitals subtracted from each other, two wave functions subtracted. Remember that each of these atomic orbitals is really a mathematical function, so all we're taking is two mathematical functions and either adding them or subtracting them from each other. And so this would be what we call the subtractive, or more often the out-of-phase combination of the two atomic orbitals. All right, so those are going to be what's always going to happen. When you mix two atomic orbitals together, you're going to get a bonding orbital and an anti-bonding orbital. Now, what's the difference between these two, besides just their mathematical forms? So one, the key difference from a physical standpoint is where is the electron density? Where is the electron most likely to be found in these two different types of orbitals? So in a bonding orbital, the electron density is greater along the bond, or in other words, in between the nuclei. And so what that means is if you put electrons into a bonding orbital, that contributes to strengthening the bond, to bringing the nuclei closer together and holding them together stronger in the bond. Whereas in an antibonding orbital, the electron density is greater outside of the internuclear region, in other words, outside of where the two nuclei are in the molecule, in the diatomic molecule. And when you start populating antibonding orbitals, you're going to actually weaken the bond and bring the nuclei further apart. So, in other words, to make the strongest bond possible, you want as many electrons as possible in bonding orbitals and as few electrons as possible in antibonding orbitals. And then the relative energies of the bonding and antibonding orbitals. So whenever we mix two atomic orbitals to make a bonding and an antibonding combination, the bonding orbital is going to be lower in energy than the atomic orbitals. And there is a bit of a, conservation of energy at play here, and then that means that the antibonding orbital must be higher than the atomic orbitals. So those are kind of the key features then of when we mix two atomic orbitals together to make bonding and antibonding orbitals. So the first type we're going to talk about, the first type of molecular orbitals we're going to talk about, the very simplest ones, are going to be what happens when we just mix together two 1s orbitals. All right, so this would be exactly what would happen, for example, in H2, where we just have a 1s orbital on each atom, and we're going to mix them together to make molecular orbitals. So as we said, you're going to always get a bonding and antibonding orbital. When 1s orbitals mix together, as we learned last time in the context of valence bond theory, the only type of bond we can form is a sigma bond. You can't form pi bonds with s orbitals. So we're going to form sigma bonds, and we're going to abbreviate the molecular orbitals then as sigma and sigma star, where sigma is the bonding molecular orbital, sigma star is the antibonding, and you'll often see subscripts to indicate which atomic orbitals were used to make those molecular orbitals. That doesn't necessarily have to be there. And then the sigma orbital is going to be, again, the additive combination of the two 1s orbitals, one from each atom, and the sigma star is going to be the subtractive combination of the two 1s orbitals. So what these would then look like pictorially is going to be, in the bonding case, you're going to have your two nuclei, and it's going to be an in-phase combination that gives you a delocalized orbital. So now the orbital, again, is delocalized over the whole molecule, over both nuclei. This would be one nucleus here, another nucleus there. And the bonding orbital has electron density in between those two nuclei, and it's an in-phase overlap of the two, so it looks like this. This is going to be your bonding orbital. In the antibonding case, you're going to have your two nuclei, and the electron density is going to be greater outside the region between the two nuclei. So it's going to look something like this. So you're going to have one lobe going that way, another lobe going that way. And because it's an out-of-phase combination, one half of the molecular orbital is going to be opposite in phase, so we'll indicate that with shading to indicate that the sign of the wave function is different on this side versus this side. And you're going to have a node then that's in between the two nuclei. So this is sort of what a sigma antibonding orbital will look like. It's going to be two 1s orbitals, but they're mixed out of phase, which then leads to electron density being greater outside the nuclei, outside the internuclear region, and this is what the antibonding one would look like. All right, so the key point, though, is that they're delocalized over the whole molecule. These orbitals do not just localize on one atom or the other, they delocalize over the entire diatomic molecule. Now, the more important thing than the shapes of these orbitals is going to be what we call the molecular orbital diagram. So what we're going to do in a molecular orbital diagram is we're going to show the relative energies of the molecular orbitals, and then once we have those orbitals ranked in terms of energy, we're going to fill them with the correct number of electrons for whatever molecule we're talking about. So for two 1s orbitals, the way that we would draw the orbital diagram is on the outsides of the diagram, you show the two atomic orbitals that you're mixing. So if it's two identical 1s orbitals, you would have two atomic orbitals at the same energy. Energy is going to be on the vertical scale here. So this vertical scale is going to be energy. So you'd have two 1s atomic orbitals at the same energy, and then we're going to show that when these mix together, you're going to get a sigma 1s orbital that's lower in energy. We're going to put those in the middle of the diagram. Then you're going to get a sigma star antibonding orbital that's higher in energy. So again, when you mix these two atomic orbitals together, you get bonding and antibonding. Bonding is lower in energy, antibonding is higher in energy. And then you often will see dashed lines that connect the atomic orbitals to the molecular orbitals to show again where these molecular orbitals come from, these ones coming from the mixing of two 1s atomic orbitals. Now, the important point of this diagram is the middle part here, because this shows the molecular orbitals for the whole molecule. So I want to highlight that in red, I guess, where really what you care about in molecular orbital diagrams is the ordering of the molecular orbitals. You don't necessarily have to show the outside part of the diagram, the atomic orbitals that they came from, although that is helpful information. It helps you understand where these molecular orbitals come from. But what's going to be key for making predictions about the properties of the molecules is to know the ordering of the molecular orbitals and then be able to put the correct number of electrons into there, as we'll see here in a little bit. All right, and a key point that I want to emphasize is that whenever you see a molecular orbital diagram, the number of atomic orbitals that you're combining, in this case just two 1s orbitals, one from each atom, is going to be equal to the number of molecular orbitals that are formed. All right. So that's going to be sort of the energy level diagram that we're going to use to put these atomic orbitals in lower to highest energy order, and then we'll fill them with electrons, as we'll see here. All right. So we're going to put electrons in here in a second, but before we do that, let's talk about then the parameters that you can determine. So once you have a molecular orbital diagram that puts the molecular orbitals in the correct energy ordering, and then you add the correct number of electrons to that diagram, what are some of the things we can determine from that diagram? So one of the key ones is the bond order. We've already talked about bond order. It's, in valence bond theory, it's typically either a single, double, or triple bond order of 1, 2, or 3. But we can use the molecular orbital diagram to calculate what the bond order is as well for diatomic molecules, and that's going to be given as 1/2 times the number of bonding electrons. So this is how many electrons in our diagram end up in bonding orbitals, minus the number of antibonding electrons. This is 1/2 times this difference. So in a typical molecular orbital diagram, you're going to have a lot of cases some electrons in bonding orbitals, some electrons in antibonding orbitals. The electrons that are in bonding orbitals, the more of those you have, the bond order is going to be higher, because those are the ones that bring the two nuclei together. The more electrons you have in antibonding orbitals, those are going to weaken the bond and then make your bond order smaller. So it's kind of that, again, competition between those two, and that's what this little equation here allows us to do, is determine the bond order numerically. The other thing it will allow us to do is say something about what types of bonds we have, either sigma, pi, or some combination. For 1s orbitals, you only have sigma, as we saw, so that's not going to really come into play here. But a little bit later on, we're going to do molecular orbital diagrams for p block elements, which are going to include both sigma and pi orbitals, and you'll be able to use the orbital diagram and how many electrons there are to figure out whether the bonds are sigma, pi, or some combination of the two. And then the key one that molecular orbital theory allows us to do accurately for diatomic molecules, which valence bond theory does not, is predict the magnetic properties. And again, there are two limiting cases here. So it will allow us to predict either that it's diamagnetic, which means no unpaired electrons, And then physically speaking, that means that it's going to be weakly repelled by a magnetic field, which is what we saw for liquid nitrogen in that video, where basically just went straight through, didn't even get suspended at all by the magnetic field. Or the other case would be paramagnetic. This means you have one or more unpaired electrons. Doesn't matter how many. It's either just going to be one of these two classifications. So one or more unpaired electrons, we call it paramagnetic. And the physical behavior, as you saw for liquid oxygen in the video, is that it's attracted to a magnetic field. So when they pour liquid oxygen through the magnets, it sort of got suspended there because it was attracted to the magnets, which is what you'd expect for something that's paramagnetic. Okay, so these are the two types of magnetic properties, something new that we haven't seen before. But once you have a molecular orbital diagram, you can easily tell if there's unpaired electrons or not, and that's going to then distinguish whether it's diamagnetic or paramagnetic. Okay? So those are the things we can tell. So let's go and start doing that then for some hypothetical and real molecules. The other thing that, as we'll see, this allows us to do is deal very easily with odd electron systems. So when we were drawing Lewis structures, we didn't really see very many at all of molecules that have an odd number of electrons. And if you try to draw a Lewis structure for something that has an odd number of electrons, it gets kind of hairy. Like, what do I do with this odd electron? Or how do I count this as a bond or a non-bonding electron or what? And so in molecular orbital theory, we don't have to worry about that because this is all going to come out straight from the diagram. So if we do the H2+, this is going to be dihydrogen with a plus charge. This would be a hypothetical ion that just has a single electron. H2 would have 2 electrons, positive charge. If we remove one, to have a total of 1 electron. And then what the molecular orbital diagram would look like, they're all going to look the same because it's just 1s orbitals. So as we said, when you mix two 1s orbitals together on hydrogen, you're going to get a sigma and a sigma star. And so this middle part of the diagram here is where we're going to put the electrons that are part of our molecule, in this case just 1 electron. And when we're filling the orbitals with electrons in a molecular orbital diagram, we're going to follow the same rules that we did for atomic orbitals back in chapter 2. So remember that when we did electron configurations for atoms, the rules that we followed were we went lowest energy orbitals first, then highest energy orbitals. We did in that order. And then also, we don't have to deal with this quite yet, but when we have degenerate orbitals, we want to make sure that we maximize the number of unpaired electrons. So for this molecule here, for H2, we just have 1 electron to put in, so we're going to put it into the lowest energy available orbital, which is the sigma 1s. So in H2+, you're going to just have 1 electron in a sigma 1s orbital, and then the bond order for H2+ is going to be, remember that the way we calculate this is it's going to be 1/2. The first number we put in is the number of electrons that are in bonding orbitals. We only have 1 electron total. It's in the sigma 1s bonding orbital. So there's 1 electron that's in a bonding orbital. There's no electrons in the anti-bonding orbital, so that part's 0, which means that we would predict this as a bond order of 1/2. So one thing you'll often predict from molecular orbital theory, which again is not easily rationalized with valence bond theory, is fractional bond orders. Not necessarily whole numbers, 1, 2, and 3, but in this case, a bond order of 1/2, or as we'll see later, you can get bond orders of 2.5, and these sort of intermediate fractional bond orders. All right, so that's what we predict for H2. If we go to, H2+, if we go to H2, the neutral molecule, yep.
You didn't do anything with the charge?
Well, I took away 1 electron, so H2 without a charge would be 2 electrons, because there's 1 electron from each hydrogen. H2 with a positive charge only has a total of 1 electron, so why we put 1 electron in this diagram. Now if we go to neutral H2, which is what we're going to do next, that would have 2 electrons. Remember, we have to count valence electrons just like we would for any molecule that we're drawing a Lewis structure of or anything like that. So H2, each hydrogen has a 1s valence electron, so there's a total of 2 valence electrons, 1 from each hydrogen atom. So in this case, we're going to have the same diagram. It's still going to be 1s orbitals that we're mixing to make a sigma and a sigma star. But now we're going to put 2 electrons in the diagram. But again, following the rules that we use for atomic orbitals, we're going to fill the lowest energy available orbitals first. Each orbital can have still up to 2 electrons, 1 spin up, 1 spin down. And so the diagram for H2 would look like this. We're going to have both electrons in the sigma 1s orbital, one with a spin up, ms equals plus 1/2, one spin down, ms equals minus 1/2. So we're going to basically fill in these middle parts of the diagram is analogous to filling atomic orbitals, but now we're filling orbitals that belong to an entire molecule, not just to a single atom. All right, and so if we calculate the bond order for H2, if we drew the Lewis structure for H2, we would just predict that it's a single bond. I hope that's fairly obvious to everyone. And if we calculate the bond order from the MO diagram, we're going to get 2 electrons now that are in the bonding orbital, still 0 electrons in the anti-bonding orbital. We didn't have to put any up there. And so in this case, we get 1/2 times 2 minus 0, which is 1. We predict that this is a single bond, which is what we would have also predicted from the simpler method. So in most cases, there's not huge amounts of disagreement between the molecular orbital theory and what we would have predicted from simpler bonding theories like valence bond theory. In this case, hydrogen being a single bond is easily predicted by both of them, okay? We can take this a little bit further now. So if we do H2 minus, or alternatively, we can think of this as helium-2 with a positive charge. Either way, we would predict that these have 3 electrons. And so if we're going to put 3 electrons into this diagram, same orbitals still, 1s orbitals mixing together to make sigma and sigma star, and then we're going to put the electrons into these molecular orbitals in the center of the diagram. Now we have 3 to put, so we're going to put the first 2 down here, but now we have no choice but to put a 3rd electron up into the sigma star 1s orbital, okay? So the bond order for this is going to be 1/2. Out of our 3 electrons, 2 of them are in the bonding orbital down here, and the 3rd electron is up here in the anti-bonding orbital now, so it's going to be 2 minus 1. Then we're going to take bonding electrons minus anti-bonding. In this case, we also then predict a bond order of 1/2. So once again, we predict a fractional bond order. This time a little bit different though, because we fill the bonding orbital, then we've half filled the anti-bonding orbital, which partially cancels out the bond and makes the bond order smaller. And then finally, if we go to He2, which has 4 electrons, now one thing that's known is that helium, which is a noble gas, just exists as helium atoms. You don't have helium bonded to itself to make He2 naturally. And one of the reasons that we call them noble gases is that they tend not to form bonds with themselves. So like, you know, all the noble gases, helium, neon, xenon, and on down, argon, xenon, and so on, all those exist as just single atoms, not bonded to other noble gas atoms in their natural state. Now let's see if we can rationalize why that is. So if we try to draw a molecular orbital diagram for He2, using again 1s orbitals as the valence orbitals, sigma and sigma star, in this case we're going to put 4 electrons in the diagram, so we're going to put 2 in this orbital and then 2 in that orbital. Remember, up to 2 electrons per orbital. So after we've added the 2 down here, we have to go to the higher energy orbital and put the last 2 up there. Once again, opposite spin to follow the Pauli exclusion principle.
Question?
Yeah.
4 electrons?
So helium-2, each helium has 2 valence electrons. It's a 1s2 configuration. There's 2 of them in the molecule. So this is basically just counting valence electrons like we would for any type of Lewis structure that we did before. So you know that if we go to the periodic table, helium is in group 2, so it's, well, it's a weird one because it's actually over here in group 8, but it's 1s2 configuration, so there's 2 valence electrons for each helium atom. He2, which has 2, is going to have a total of 4 valence electrons then. All right, so then we have 4 valence electrons, and when we calculate the bond order for this, 1/2, we have 2 electrons in the bonding orbital. We also have 2 electrons in the anti-bonding orbital, and so what you predict is a bond order of 0. Now, what does it mean to have a bond order of 0? To have a bond order that's not a number, but it's just 0? What it means is that the molecule is unstable and does not exist. So anytime you predict a bond order of 0, it basically means that that molecule does not form, those 2 atoms don't form a bond with each other, and you don't make the stable He2 molecule. And that's exactly what we know experimentally. We don't observe helium bonded to itself to make He2. We never see that. And that's because in order for that to happen, it would have to have a bond order of 0, which doesn't exist. So when the bond order is 0, it basically means it's more favorable for the 2 atoms just to stay apart on their own as opposed to trying to come together and make a bond, because when they try to do that, you don't get a net bond. You get the sigma and the sigma star that completely cancel each other out. So this allows us to, again, predict some things about noble gases as well. So that kind of takes us through the case with s orbitals, where again, it's just this simple diagram. So if we ask you anything on homework assignments or tests about hydrogen or helium, just the s elements, then you're going to just use these very simple diagrams. But what about if we go to the p block of the periodic table and start talking about atoms that have both s and p orbitals? And what do we do with the p orbitals then? So with p orbitals, there's two possibilities now. So one is that, and we kind of saw this to some extent in valence bond theory as well, but with p orbitals, you can form also sigma molecular orbitals as well. What we're going to do is we're going to assume that the bond axis is the x direction. So remember that we have px, py, and pz atomic orbitals. We're going to assume that the direction along the bond is x. I don't think this is the most conventional way, but this is how your book does it, I believe, so I'll stick with it. And so what that means is that if we take two px orbitals, two p orbitals that are aligned along the direction of the bond, and we combine those, we're going to make sigma molecular orbitals, where the bonding orbital would be an in-phase combination of the two px orbitals. So what you would get is one px orbital, and I'll put the nucleus here at the center of it in red. So you have one px orbital making a linear combination with another px orbital. And when we say an in-phase combination, what that sort of means is that we're taking the two orbitals and we're lining up the phases that are the same. So these have remember p orbitals have two different phases, two different lobes in their orbital. We're going to take the two that are the same and line them up with each other and bring them together. And what that's going to give us then is a sigma bonding molecular orbital that looks something like this. So we're going to have, this is a little bit hard to draw, so give me a second. We're going to have, it's going to look something like this, where basically the two p orbitals combine, and you're going to get in-phase overlap in between the two nuclei. The nuclei are going to basically be here and here, and you're going to get this sort of, again, sigma overlap in between the two nuclei. That's going to result in the formation of a sigma molecular orbital. And just like we have for s orbitals, anytime you mix two p orbitals together, you also get bonding and anti-bonding. So if we get a bonding combination of px orbitals, we will also get the anti-bonding combination, which is going to be the subtractive combination px minus px, an out-of-phase combination of the two. So in this case, we're going to get a px, and we're going to add that out of phase to another px orbital, meaning we're going to flip the phase of one of these two, subtract them from each other. And so when you do that, you're going to get a molecular orbital that has a node in between the two nuclei, and you're going to have most of your electron density outside of where the two nuclei are. So you'll get something that looks like this, a node, and then the other half of your orbital on the other side of the node, where you're going to have a nucleus there, and then the phasing of the orbitals is going to be alternating. So you're going to have basically an out-of-phase overlap between the two, such that you get a node in between them. Remember, anytime we change phases, we have to have a node. So if we put an out-of-phase overlap between the two, in between the nuclei, there's going to be a node in between the nuclei, meaning that the electron density is greatest outside of where the bond is. So this would be your sigma star p, again, a sigma star orbital derived from p orbitals. Shapes of the orbitals, again, not super important, but it is important to know that for p orbitals, this is one way that we can mix them. We can take them together head-to-head along the bond axis, and that's going to form sigma and sigma star bonding and anti-bonding orbitals. Now, the other way to mix p orbitals is to make pi molecular orbitals. So we talked about last time that another way that p orbitals can overlap in the context of valence bond theory is to make pi bonds. And the same thing happens in molecular orbital theory, where now we're making delocalized pi orbitals that are going to be delocalized over the entire molecule. So as one example, so we said px was going to be the ones that are aligned along the axis. If we look at the two perpendicular p orbitals, py and pz, we can do it with py first. Let's say that the y-axis is basically this direction, the vertical direction on this page. So if that's y, the one set of pi p molecular orbitals is going to be taking the two py orbitals and combining them in phase and out of phase. So when we do this, in this case, we're going to get a side-to-side overlap of the two orbitals. So we're going to take two py molecular orbitals, and they're going to overlap side to side. And what you're going to get then is a nucleus here, nucleus there, And the pi molecular orbital is going to have electron density that's above and below the two nuclei. So you're going to get sort of a delocalized lobe above, a delocalized lobe below. Ideally, they should be symmetric, and they didn't do a great job. And they're going to be opposite phase because they come from a p orbital. But that's what your delocalized pi molecular orbital looks like. It's no longer two separate p orbitals. It's a delocalized orbital over the whole molecule that has electron density above and below the plane, again indicating that it's a pi orbital. And there's in-phase overlap between the nuclei, making it a bonding orbital. And if you're going to get a bonding pi orbital, you also get the anti-bonding combination. We always have bonding and anti-bonding coming together. So the anti-bonding combination would be py minus py. So two p atomic orbitals mixed in an out-of-phase fashion is going to give you a molecular orbital that looks something like this, where you have your two nuclei here, and also the individual nuclei and the atomic orbitals being there. And then what this is going to look like is, because they're going to be added out of phase, you're going to get electron density that's more outside the nucleus with a node in between. And you're going to have, again, the opposite lobes sort of lined up with each other in this way. And so because you have destructive overlap between the two orbitals, you're going to get a node in between. And the bond would be along this axis, but you're going to have no electron density between the axis, and this would be an anti-bonding orbital. So this was your pi bonding orbital. This is your pi star anti-bonding orbital. Now what happens, though, is I showed you this for py. You also have the pz orbitals, which are going to be harder to draw, and I'm not going to try to, because those would be the p orbitals that basically come straight out of the page towards you guys. And what you're going to get with the pz orbitals is the same two molecular orbitals, pi and pi star. So the same thing happens with pz. Which is going to then result in two degenerate pi and pi star orbitals. So as we'll see when we draw the diagram here in a second, whenever you have pi molecular orbitals, you're going to get two degenerate orbitals at the bonding level, the pi p, as well as two degenerate antibonding pi star orbitals. And the reason for that is because py and pz both overlap in this way to form pi and pi star. The only difference is the orientation of the orbitals. So the ones that I've drawn in the plane of the page here would be the py molecular orbitals. The ones that come from pz would look exactly the same, but they would just be rotated towards you guys, facing out like this, with one of the lobes coming out towards you, one of the lobes going back away from you into the board. So they look identical, they're just rotated 90 degrees from this. And they're going to be degenerate then, so you're going to get a set two pi orbitals that are degenerate, one from py, one from pz, and then two pi star orbitals at a higher energy that are degenerate with each other, one from py, one from pz. So what that looks like then in the diagram, and as we'll see for the p block elements, there's actually two diagrams we need to consider. So one is for the second half of the p block. So if we go to the periodic table, to remind ourselves, this is the p block of the periodic table. We're going to primarily be doing this for these 6 2p elements here. And there's going to be two slightly different orbital diagrams depending on which elements we're talking about. So the first one we're going to deal with are for the second half of the p block, oxygen, fluorine, and neon. This one has a more intuitive ordering, in my opinion, of the orbitals. We'll talk a little bit later about the orbitals for boron, carbon, and nitrogen, which come in there's just one little difference between those that we'll highlight. But for now, we're going to start with the second half of the p block. And so basically what dictates the ordering of these orbitals is a couple of things. So first is that in O2 we have 2s and 2p atomic orbitals to consider now. Remember that the valence electrons in oxygen are in both 2s and 2p orbitals. So you have both of those to consider in this diagram. And then if we go to the 2s orbitals, just like 1s orbitals, the 2s orbitals can only overlap to make sigma and sigma star. So this part of the diagram down here is going to look identical to what we did for the s orbitals earlier. The 2s orbitals in oxygen are going to overlap to make sigma 2s and sigma star 2s. So again, what we really care about is primarily the ordering of the orbitals in the middle part of the diagram, but this also allows us to show the atomic orbitals that they derive from. So we're going to get a sigma and a sigma star that derive from the 2s orbitals. And then in the two p orbitals, as we just said, there's two possibilities. You're going to either get sigma and sigma star or pi and pi star, depending on which p orbitals you're talking about. Now the question is, what is the ordering of the energy of those orbitals? And to help us think about that, we need to introduce a concept that I haven't really discussed yet, which is that one thing that determines, so when you have two atomic orbitals that overlap to make molecular orbitals, we said that the bonding orbital goes lower in energy, the antibonding orbital goes higher in energy. What determines how much lower and higher those orbitals go is how strong the overlap is between the two orbitals. All right, so if you have a really strong overlap between two atomic orbitals, your bonding orbital is going to go way down in energy and your antibonding is going to go way up in energy. If the overlap between two atomic orbitals is weaker, they're not going to be perturbed as much. So if we think about the difference in the p orbitals, if you have sigma versus pi, if you're talking about a head-to-head overlap sigma or a side-to-side overlap in pi, which one do you suppose is a stronger overlap between atomic orbitals? Sigma or pi? Sigma, good guess. Good answer. All right, so it sounded way too confident to be a guess, so I think you were definitely on that one. All right, so sigma is a stronger overlap, and so what that means is that the sigma bonding and sigma antibonding molecular orbitals are going to spread apart further in energy. So your 2p orbitals, you're going to form a sigma 2p that's lowest in energy and a sigma star 2p that's highest in energy. Okay? So that's going to be what you have for the sigmas. And then the pi orbitals that form from the 2p, they're not going to split as much because the pi overlap is weaker. So your pi 2p is going to be here and your pi star here. And so this is what I consider to be the more intuitive ordering of the 2p orbitals, because your sigma orbitals split way further apart, which is why the sigma goes to the lowest and the sigma star is the highest. And then your pi orbitals don't split as much because the overlap is weaker. And so that's going to dictate then the ordering of these orbitals. So now we have the correct ordering of the orbitals in our diagram. And if we're going to talk about O2 first, how many valence electrons does O2 have? I heard someone say 12, and that's correct because we're in group 6 for oxygen. So each oxygen has 6 valence electrons. So that means dioxygen would have a total of 12, 2 times 6. All right, so we have 12 valence electrons to put in this diagram. And once again, we're going to just follow the rules for populating orbitals. Lowest energy first to highest energy. And now if we get to any degenerate orbitals, we're going to make sure that we maximize unpaired electrons. So as we go through this and do 12 electrons, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let me remove that label so it's out of our way a little bit. All right, so that's the diagram that we get with now 12 electrons in it. And a couple of things that come out of this is we said at the beginning, we showed that experiment on YouTube where we concluded that O2 is paramagnetic, even though we wouldn't have guessed that from valence bond theory. And what you see is that in this diagram, there are 2 unpaired electrons, meaning that O2 is in fact paramagnetic. All right, so the 2 unpaired electrons that we have, because of the degenerate pi star orbitals that get filled last, O2 would be predicted to be paramagnetic, which is what we observe experimentally. So again, we now have a better match between experimental results and predictions from our model, which means that this model is likely superior to the previous model that we were using. All right, so this is one of the crowning achievements of molecular orbital theory, was that it allowed us to more accurately predict the magnetic properties of diamagnetic molecules like O2. Okay? All right, and anytime, you guys might not get as excited about science as I do, but maybe someday you will. Anytime you get a match between your model and your experiment, that deserves an exclamation point, so I'm going to put it there. So that's what we see, a good match between the experimental result, the magnetic properties, and the model, which predicts that it would be a paramagnetic based on the unpaired electrons. Now, we also predicted from valence bond theory that we would have a double bond in O2. Let's see if that is also predicted or not by molecular orbital theory. So the bond order in this molecule is going to be, again, 1/2. Now we're going to count how many electrons are in bonding orbitals. There's 12 total, so how many of those 12 ended up in bonding orbitals? We have these 2 down here that are in sigma 2s, 4, 6, 8, so 6 more that are in the sigma and pi 2p's. So a total of 8 of our 12 electrons are in bonding orbitals. And that should mean that the other 4 are in antibonding orbitals, and we'll see that these 2 are in an antibonding orbital, and these last 2 that we put in up here are also in an antibonding orbital. Antibonding meaning one that has a star next to it. So 1/2 times 8 minus 4 gives us a bond order of 2. So that's not at odds with what we would have predicted before. So the bond orders typically do match up between valence bond theory and black orbital theory, and they do here. The other thing that we can write from this is an electron configuration. So in a lot of the homework questions, you'll be asked for, like, what is the electron configuration of O2, the molecular orbital configuration. And so you write this in a lot of the same way that you would an atomic configuration, where you just list the different energy levels and then you put how many electrons are in each energy level. So the way that we would write it for O2 would be we'd have sigma 2s with 2 electrons in it. So you'd write sigma 2s2. Then you'd have sigma star 2s also with 2 electrons. You have a sigma 2p that has 2 electrons in it. Our pi 2p has a total of 4 electrons in it. And then our pi star 2p has a total of 2 electrons in it. So that would be how we would write the electron configuration for O2. And what you'll see is that the sigma and the sigma star cancel each other out, and then one of the pi bonds cancels out with a pi star, so because we have 4 electrons here, 2 electrons here. So in net, we have a sigma and a pi bond, as we would predict for double bond as well. All right, but that's what we get for this one. This is sort of the things we would ask you primarily would be magnetic properties, bond order, or overall electron configuration. So if we do it now for F2, we're going to use the same diagram because we're still in the second half of the P block of the periodic table. This time for F2, the only difference is the number of electrons. Instead of being 12 is 14, because fluorine is group 7, so each one's going to contribute 7 valence electrons. And we're going to have the exact same diagram. So if we include the atomic orbitals in the diagram, which we don't necessarily have to do, we have 2s and 2p. And the 2s is going to mix to make sigma and sigma star. And the 2p is going to mix to make sigma and pi. And then pi star and sigma star up here. All right? So you're going to want to get very familiar with the ordering that these molecular orbitals come in. That's the important part, is to know what order these center orbitals, these molecular orbitals come in, so that we can fill them correctly with electrons. So once you have them in order, then we just have to dump our 14 electrons in, going from lowest to highest energy in this diagram. So we're going to go 2, 4, 6, 8, 10, 12, 14. So in this case, we've completely filled the pi star 2p. So this time we would predict that F2 is diamagnetic because there are no unpaired electrons in this diagram. We see that all the electrons ended up paired up, even at the top level. And that's also true. F2 is a diamagnetic molecule, so that matches the experiment. The bond order for this would be 1/2. We have a total of 14 electrons. We still have only 8 of them that are in bonding orbitals. 2, 4, 6, 8 are in orbitals that don't have a star next to them. The other 6, these 2, and then these 4 up here, are in antibonding orbitals, orbitals that have a star. So we're going to subtract 6 as the antibonding electrons, and that gives us a bond order of 1. So we would predict a single bond in F2, which is also what we would have gotten from simpler bonding theories. And then the electron configuration for this would be sigma 2s2, sigma star 2s2, sigma 2p2, pi 2p4, and then pi star 2p also has 4. So again, this is just writing an electron configuration which shows the different orbitals that we have, the different energy levels that we have, with how many electrons each of them includes. All right? And then finally, the last one we'll do in this series is neon 2. Now again, neon is a noble gas, so the prediction would be that neon doesn't like to bond to itself. Let's see if that's the case. So if we quickly fill in this diagram, 2s, 2p, and then sigma, sigma star, sigma, pi, pi star, and sigma star. You'll get really good at doing this the more you practice. So these are going to be the orbital levels, same as before. Now we just have different number of electrons. This time 2 group 8 elements, so it's going to be 16 valence electrons. And what you'll see in this case is that we end up filling the entire diagram. So the most, don't freeze again. The most number of electrons that we can put into this diagram is 16, so we're going to fill up the entire thing with our 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. Okay, so that's completely filled. But if we try to calculate a bond order for this, what we have now is we still have 8 electrons in bonding orbitals, but now we also have 8 that are antibonding. These 2, 4, 6, 8. 8 of our electrons are in antibonding orbitals. And so we predict a bond order of 0, which means that this is an unstable molecule. So just as we saw for helium, you can't make stable molecules with noble gases. You can't take 2 heliums or 2 neons and try to make a diatomic because you predicted the bond order is 0, meaning that the molecule just doesn't exist. All right, so that's what we get for neon 2, which sort of matches what we saw for helium earlier. All right, so any questions on those diagrams? Yep.
So for the previous diagram, you wrote out, I guess, a notation line of text.
This one?
Yes. What is indicated by your superscripts?
The superscripts is how many electrons are in each of those orbitals or energy levels. So in the sigma 2s, we see that there's 2 electrons. We put a 2 there. In sigma star 2s, there's also 2 electrons, so that gets a 2. The sigma 2p has 2 electrons, so we put a 2 there. Now when we go to pi 2p, we see there's a total of 1, 2, 3, 4 electrons at that energy level. Pi is a degenerate energy level, so it can have up to 4 electrons in it. So there's a 4 there, indicating that there's 4 pi electrons. And then the pi star also has 4, and so we put a 4 there, indicating that there's 4 electrons in that orbital as well. All right, anything else? All right, so what we're going to move on to now is not too different, but if we go to the first half of the p block, so that would be the boron, carbon, and nitrogen elements, there's one key difference in the diagram. So we're still going to be using 2s and 2p atomic orbitals to formulate these molecular orbitals that we're getting from mixing them. And at the bottom part of the diagram, the sigma and the sigma star 2s are the same. So the 2s orbitals mix together in the same way. But the difference here is that when we get to the 2p level, what we'll notice is that the pi 2p comes first and then sigma, which is the opposite of what we saw in the previous diagrams. Now the reason for this is complicated, so I don't want to dive too deep into this, but basically what happens is that in the first half of the p block, boron, carbon, and nitrogen, the 2s and the 2p atomic orbitals are closer in energy to each other. And so then what happens is that the sigma 2p is able to interact as well with the 2s orbitals. They all have sigma symmetry. They're all forming sigma bonds. And so you don't just have simple s molecular orbitals and p molecular orbitals. You have some mixing between the s and the p. And that basically drives up the energy of this sigma 2p orbital. Now we don't expect you guys to know the reason for that. It's, again, a pretty advanced thing dealing with SP mixing and concepts and symmetry that are beyond the scope of this course. But what happens, and what you need to know happens, is that the pi and the sigma 2p switch their order. All right? Pi star 2p and sigma star 2p stay the same. So the only thing that switches then is going to be the order of these 2 orbitals here. All right? So those 2 switch for the first half of the p block. For B2, C2, and N2. Again, that being the first half of the P block, P1 through P3. Okay? So that's the only thing you have to remember for these elements, that these 2 switch. Now, in terms of determining the bond order, that's not going to hurt you if you mess that up, because these are both just bonding orbitals that are flipping positions, so you'll still get the same number of bonding and anti-bonding electrons. But what happens is if you don't remember to flip the order of these orbitals, you will very likely predict the number of unpaired electrons incorrectly, okay? Because you're going to switch the ordering of the singly and double degenerate orbitals, and then when you populate them with electrons, you're going to get different numbers of unpaired electrons. So for predicting the magnetic properties, the diamagnetic or paramagnetic part, it is very important to have these in the correct order, okay? So that's why I want to make sure I emphasize it and point it out here. That's the only difference then between, again, the first half and the second half of the p block is the order that these 2 orbitals come in. So you do need to remember that. But so now if we populate this one with electrons for B2, boron is in group 3, so each one has 3 valence electrons, total of 6 for B2. And now we're going to put 6 electrons in this diagram, so we're going to get 2, 4, and then at this level here, 5, 6, making sure that we keep the maximum number of unpaired electrons, leaving it like that. So we would predict that B2 is paramagnetic. It's not a particularly stable molecule, but it has been observed. The bond order of this molecule, and here's something that's weird about this molecule that we'll see here in a second. So the bond order, if we predict it, is going to be 1/2. Out of our 6 electrons, these 2 and these 2 are in bonding orbitals. So 4 of them are in bonding orbitals. These 2 electrons are in the sigma star 2s antibonding orbital, so we're going to subtract 2. 1/2 times 4 minus 2 is 1. So we would predict that this is a single bond, and based on valence bond theory, if we said it was a single bond, what kind of bond would that be? Sigma. But if we look at the diagram here, we don't have a sigma bond because our sigma 2s and our sigma star 2s cancel each other out. In net, what we have is a pi bond. So even though it's a single bond, it's actually predicted to be a pi bond. So this is something, again, that's a little bit different between valence bond theory and molecular orbital theory. Valence bond theory will predict if it's a single bond, it has to be a sigma. But in this case, the bond order is 1, but it's going to be predicted to be a pi bond. All right. So not something we would have seen before. We can write the electron configuration for this as sigma 2s2, 2 electrons in the sigma 2s. Sigma star 2s also has 2. And then our pi 2p has 2 electrons as well. So the 6 electrons divided up into 3 different energy levels. So that's our electron configuration. But the weird part about this is that even though it's a single bond, we predict it's a pi bond. Again, the most important things for you guys to be able to do are predict the magnetic properties and the bond order. If you can do that, that's what 90% of the molecular orbital questions are going to be about. But we can look a little bit further, dig a little bit deeper, and see that it actually is a pi bond, even though the bond order is 1. All right. And if we go to C2, we're actually going to see some similar weirdness in the molecular orbital diagram for C2. Again, not a particularly stable molecule that's observed easily, but has been studied presumably under some weird conditions. So C2 has 8 electrons. It has the exact same orbital diagram as B2, just different numbers of electrons. So we're going to mix the 2s and the 2p to make sigma and sigma star 2s. And then again, for this part of the periodic table, we're going to flip the order of the pi and sigma and 2p and put pi first in the 2p orbitals. Pi star and sigma star not changing. And so now we need to fill this with 8 electrons. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8. And we get that this is a diamagnetic molecule. There are no unpaired electrons. Again, it's important to have the ordering of these 2 orbitals correct to make that prediction accurately. The configuration is sigma 2s2, sigma star 2s2, and then pi 2p has 4 electrons in it. So that's going to be the configuration. And then the bond order that we would predict for this. Now we have 6 electrons in bonding orbitals. These 2 down here, plus the 4 that are in the pi 2p. So all 6 of those electrons are bonding. These 2 electrons in sigma star 2s are still antibonding. So it's going to be 1/2 times 6 minus 2, giving a bond order of 2. And again, there's some weirdness here because in valence bond theory, if we had a double bond, we would say that it's 1 sigma and 1 pi. But what we'll see here is that both of these bonds are actually pi because the sigma and the sigma star 2s, once again, cancel each other out. The only net bond that we have is 2 pi bonds, 2 filled pi orbitals. So it's a double bond because the bond order is 2, but the prediction is that it's going to be no sigma bonds and 2 pi bonds, contrary to what we would predict in valence bond theory. Again, this is not something we're going to emphasize a lot in this course, but it is something that is, different about molecular orbital theory, and one of the predictions that molecular orbital theory makes that you would never get from valence bond theory, that you can have different arrangements of sigma and pi than what I told you last time. All right, so that's C2, and then finally the last one in this series is N2. Now, if we drew the Lewis structure of N2, we would predict that it's a diamagnetic molecule with a triple bond, and this molecular orbital diagram really has no weirdness associated with it. So in N2, we're going to put 2 electrons into our diagram. So there's a lot of repetitiveness here. We're just putting different numbers of electrons in. So we have sigma. Again, the middle part of this diagram is the important part, the ordering of the molecular orbitals. Pi coming before sigma and N2, although for this one it doesn't particularly matter because we're filling all these anyways, we'll see. All right, so those are the ordering of the orbitals, same as before. This time we get 10 electrons, so we're going to go 2, 4, 6, 8, and then 10. And so what we've done in N2 is we've filled all the bonding orbitals, sigma 2s, pi 2p, sigma 2p, while only filling one of the antibonding orbitals. This is going to give us the maximum bond order, as we'll see here in a second. So it's diamagnetic, and the bond order is going to be 1/2. We have 8 of our 10 electrons are in bonding orbitals. 2, 4, 6, 8 of those electrons are in bonding orbitals, and only these 2 are anti-bonding. And so we get a bond order of 3, triple bond, which is what we would predict from valence bond theory. A bond order of 3 is the highest that you can get in a diatomic molecule with this type of orbital diagram. There's no other way to get a bond order that's higher than 3. And the configuration would be sigma 2s 2, sigma star 2s has 2 electrons in it, our pi 2p has 4, and our sigma 2p also has 2 electrons in it. So this would be the right way to write the configuration for that. So really no weirdness in N2. Diamagnetic, triple bond, 1 sigma, 2 pi is exactly what we would predict from valence bond theory. So there are some cases where the 2 line up very well, but there's some other cases, especially for some of these weirder, more esoteric molecules, where molecular orbital theory allows us to make some predictions that we wouldn't get very easily from valence bond. And then finally, the last thing I want to cover is, again, the possibility of a fractional bond order in p block elements as well. So if we had N2 with a positive charge, I think it's called the diazonium cation, not that that's important. In this case, it's going to be 2 nitrogens with 5 valence electrons for a total of 10, but we're going to take 1 away for the positive charge, so we're only going to put 9 electrons in. And once again, molecular orbital theory is one of the key advantages is that it allows us to deal with odd electron species very easily, much more easily than we could using valence bond theory. So if we're going to have the same orbitals available, because it's still nitrogen, so it's going to still be 2s and 2p, and we're still going to form the same molecular orbitals in the same order. All right, so those are the same exact orbitals, so nothing new there. This time we're going to put 9 electrons in. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, and then 1 last one goes up here. So we do have 1 unpaired electron. Anything that has an odd number of electrons is paramagnetic, so you don't have to think about it. But this would be paramagnetic. But it has an odd number of electrons, so it has to be. If it has an even number of electrons, it could be diamagnetic or paramagnetic. If it has an odd number of electrons, it has to be paramagnetic. There's no way to pair up all the electrons. And then the electron configuration for this would be sigma 2s2, sigma star 2s2, pi 2p4, and then sigma 2p now just has 1 electron in it up there. And here if we predict the bond order for this, 1/2. Out of our 9 electrons, these 2, 4, 6, and 7 are in bonding orbitals. And it's just, once again, these 2 sigma star 2s's that are anti-bonding. So what we predict from this is a fractional bond order of 2.5. All right, so again, valence bond theory allows us to deal with odd electron species much more easily and predict what the bond order would be, which is going to be something that's, in this case, a fractional bond order of 2.5. All right, so hopefully we've beat that dead horse enough. The last topic that I want to cover, though, we're not quite done yet, is the concept of delocalization. So for most of molecular orbital theory, the vast majority of what we're going to do is going to be diatomic molecules like we just covered, put the orbitals in the correct order, put the electrons in, answer a question about bond order or magnetism, really all variations on that same theme, not a whole lot that we're going to do with it. The last thing we're going to cover, which is just, it's a little bit out there, I suppose, for this part of the course, but it is in your book, so I want to make sure that I go through it just a little bit, is the idea of what's called delocalization. Now, we talked about resonance already. So resonance is the idea that when you have certain molecules with double bonds, in some cases the double bonds can be put in different locations, and what that really means is that that double bond, that pi bond, is not localized between 2 atoms, but is delocalized over the entire molecule. And we're going to take that a step further here and talk about that in the context of molecular orbital theory, at least at a very basic level. We don't expect you to know a lot of depth about this. So let's consider this organic molecule benzene, C6H6, which has been in the news recently in Houston because I think it was last summer it was accidentally released into the atmosphere during a fire at a chemical company of some sort. So it got a lot of attention. It is carcinogenic, not the safest thing in the world, but I think in that case the level of freak out about it was perhaps unjustified. Anyway, what benzene is it's a hexagon with 6 carbon atoms in it. Each carbon has 1 hydrogen associated with it. So each carbon has a CH bond. And then it's going to have, to make sure that we can complete the octet and carbon, each carbon right now only has 3 bonds. And so what we're going to do is we're going to have alternating single and double bonds. So it's going to be a double bond there, single bond there, between the 2 carbons, double bond, single bond. But as you might recognize, there are 2 possible resonance structures I can draw. So I put the double bonds here, here, and here, but I could have just easily moved them over 1 position to make them here, here, and here. So there's going to be 2 equivalent resonance structures where we can, again, make the hexagon. With the hydrogens on each carbon. And in the alternate resonance form, we just move the double bonds over 1 position to make it here, here, and there, okay? So 2 equivalent resonance structures that just, again, vary with respect to the positions of the double bonds. Another way to draw this, as you'll see sometimes, is, I'll still keep the carbon and hydrogen shown explicitly to not confuse you guys with any shorthand, but basically, another way of drawing this is, ran out of room there, but there's a hydrogen down there. You draw just a circle in the middle of the ring to indicate that you have delocalized pi bonds. Because remember, these resonance forms don't mean that the pi bond is here sometimes and here sometimes. What it really means is that these 6 pi electrons, these 3 pi bonds, are basically just delocalized over the entire molecule. All right? And a couple of other things. All the carbon-carbon bonds are equal. Because again, it's alternating single bonds. It's really not a single or a double bond. It's in between. It's a 1.5 bond is the correct bond order. And so all of these CC bonds are equal in length because they're all the same. And another important thing is that in terms of valence bond theory, we would predict that all the carbon atoms are sp2 hybridized. Each carbon has 3 things attached to it, 2 other carbons and a hydrogen, making it sp2 hybridized. All right, so really the best way to describe the bonding in benzene is going to actually be to use a combination of valence bond theory, so hybridization, saying that these are sp2 hybridized, along with molecular orbital theory. So the sigma bonds in benzene are going to be most easily modeled and best modeled with valence bond theory. So we said that each of these carbon atoms is sp2 hybridized. So what I'm going to attempt to draw, and it often takes me more than one try, is for each carbon atom we're going to have a set of sp2 orbitals. Now remember what that means is that each of those sp2 orbitals is going to be arranged into a trigonal plane, each 120 degrees apart from each other. So each carbon atom is going to have a set of orbitals that are arranged like this, 120 degrees apart. And what you're going to have is that the sigma bonds between the carbons, remember that each carbon has a sigma bond as well as the alternating pi bonds, the sigma bonds between carbon are going to involve these sp2 orbitals. So you're going to get overlap between sp2 orbitals to make the sigma bonds throughout the ring. So you have a carbon there with its sp2 orbitals. All right, so that's one of your sigma bonds there, and then you're going to have another carbon down here that's overlapped to that. CCC, God. So this carbon is sp2 hybridized. The problem is if I don't space these out correctly, I just don't close the ring very well at the end, which I think is what's happening here. So, and then you're going to have a carbon here with sp2 orbitals, making a sigma bond with that one. And then this one is going to overlap with sp2 orbitals on the next carbon. sp2 orbitals on this carbon, and I didn't do a terrible job. They come back around and connect that way. So the point of all this is that each of the carbons is sp2 hybridized, and 2 of its sp2 orbitals are going to be overlapped with adjacent carbon atoms, sp2 orbitals, to make the sigma bonds. And then you're also going to have overlaps with all the hydrogen atoms, their 1s orbitals, to make the CH bonds. So all the sigma bonding in this molecule is best described with valence bond theory, where you have sp2 hybridized carbon atoms, and they're going to form three sigma bonds each, 2 to carbons, 2 to hydrogen. And so you're going to have this ring of carbon atoms with this sp2 orbitals. I didn't do a perfect job of drawing it, but the idea here is that each of these carbon has a set of 3 sp2 orbitals that are interconnected to make the ring, and then there's the one that sticks outside that's going to bond to the hydrogen atom. So that's how we can describe the sigma bonds, but the pi bonding is best described using delocalized molecular orbitals. So basically what happens in the pi bonds in benzene is that because each carbon atom is sp2 hybridized, remember that when you have sp2 hybridization, you also then would have one unhybridized p orbital on each carbon, because each carbon started with an s orbital and 3 p orbitals. We hybridized the s orbital with 2 of the p orbitals to make these sp2 hybrids that we just drew up here. That means there's one more p orbital that's left over that's not hybridized. And so what those p orbitals are going to look like is basically you have your hexagon of carbon atoms, which I'll draw as just a hexagon here. And there you go. Okay, so sort of trying to draw a little bit of a tilted hexagon. Each of these corners here is where one of the carbon atoms is. The carbon atoms has sp2 orbitals that are in the plane of the hexagonal ring, but then you also have a perpendicular p orbital at each of those positions, okay? So at each carbon, you're going to have a perpendicular p orbital. And then what happens is you're going to have pi overlap both, and I guess I should draw the opposite phase as well to keep that consistent with how I've done it before. So each of these carbons has a perpendicular p orbital, perpendicular to the plane of the ring, and you're going to get overlap of the lobes above and below the plane of the ring to make a set of pi molecular orbitals. Now in reality, you have 6 p orbitals overlapping, so you're going to make 6 pi molecular orbitals. It's beyond the scope of this course to talk about the energy ordering of those pi molecular orbitals and how they arrange themselves and what they look like. But the point is that you're going to get this pi overlap above and below, and you're going to make a series of 6 pi delocalized orbitals where you're going to have overlap around the entire ring of the molecule. And that's the best way then to describe the pi bonding in these molecules, which you will get a lot more detail about if you ever take organic chemistry and go beyond that. All right, so that takes us to the end of what I want to cover today. Just a little bit of a brief introduction about delocalization that's in your textbook, but not too much depth that we're going to go into there. So we finished chapter 4, which is our goal, and next time we're going to start chapter 5 with a big change in direction. Last question? How would we ask a question about something like this on the exam? Mainly just definition-based or concept-based about, how do the pi orbital, how do the p orbitals in benzene overlap? You want to know they overlap in above and below the plane to make a delocalized pi bond, something like that. It's going to be very conceptual and very basic.